All right, this is the comparison tests of our series tests. This one is split into two sections, so more than likely we're going to do this in two videos. We'll have to see how long they run, but I think we'll get it in two just fine. There are two types of comparison tests. Now, the one thing about the comparison test is it's not going to tell us anything other than convergence or divergence of a series. It will tell us that information. However, it's not going to tell us anything about the sum. So these are just tests for comparing, for telling convergence and divergence. Okay, so the first thing we're going to talk about is there are two different types. There's one which is called the direct comparison test, and then there's one which is called the limit comparison test. As far as I'm concerned, personally, I think the direct comparison test is the most easy to understand. It definitely makes the most sense, not necessarily the easiest to do. Um, the limit comparison test, however, is far easier to do. Um, and as long as you have somewhat of an understanding of how everything's been working so far, then it's really not that more difficult to understand, but it definitely takes some background knowledge. Okay, so here's the general idea of the direct comparison test. What it says, and then I'm going to give you a graphic illustration of this. It says, let 0 be less than a sub n, which is less than or equal to some b sub n. So a sub n and b sub n here are different series. Okay, these are different infinite series. So one of them is less than the other one, and they're both greater than 0. For all integers n beyond a certain value, so it doesn't have to start at n equals 0, n equals 1. It can start at n equals 5, or whatever we need it to start at. But basically, from there on, this is going to be the case. What it says is this. It says that if the series b sub n converges, then a sub n converges. And then it says, conversely, if a sub n diverges, then b sub n diverges. Okay, now let me show you what that means. So if I were just to kind of construct a very simple graph here. Now remember, the criteria is that both of these things are greater than 0, and we're going to know something about both of these series. So the first one says, if b sub n converges, so we're going to call this, this series that I'm getting ready to draw right here, b sub n. And it's going to look something like this. So as you know, for something to converge, its terms, that's not very good. Let me draw that again. Its terms must approach 0. Wow, I am not doing very good. I'm just wobbling all over the place here. Try one more time. All right, better. So the idea is that this series does something like this. It will approach 0. All of its terms are going to approach 0. And we're telling you that this is converging. So this is b sub n in red. And then in this green that I'm getting ready to do here, we're going to call that a sub n. And what it says is this. It says that if b sub n converges, a sub n converges. We'll look at how they compare. A sub n is less than b sub n, which means at some point it's got to be down here. It's got to be less than this. Well, think about this. B sub n's terms approach 0 fast enough so that it converges. Anything less than this also has to approach 0 fast enough for its terms to converge. And that is the general idea. So what it's saying is, if I know that this function right here, b sub n, converges, anything underneath of this also has to converge. It's going to approach 0 fast enough that it's going to give us some kind of a sum. It's going to converge. Hopefully that makes sense. Now, conversely, we can't say that if we know that b sub n converges and a sub n is up here somewhere, we can't say that this converges. It might, but we don't know that. What we can, however, say, going back to number 2 here, is if we kind of change this around, I'll draw another graph here. This will be representing number 2. Now a sub n, we're saying diverges. A sub n we did in green, so let's keep that consistent. So now I'm telling you that whatever a sub n is, looks like something like this. This is a sub n. I am telling you this is divergent, so this thing is not approaching 0 fast enough. If that's the case, and we know b sub n, which is already has to be the same or greater, then any function up here also has to diverge if I know that this one here diverges to begin with. So let's go ahead and put that one in red. So b sub n, which is greater than a sub n, also has to diverge. This is for number 2. So let me go ahead and label these. This is for 1. This is for 2. Case 1, case 2. So again, think about this. Let's go back to case 1. If we know that whatever series this is converges, anything less than that series also must converge. And of course, this is following the criteria. These are both greater than 0. We're not talking about things which are negative down here. This one up here says that if I know that I have a divergent series, which is a sub n here, the green one, anything above that also has to diverge. Because if this one doesn't approach 0 fast enough, anything above that will not approach 0 fast enough to converge. So again, I think the concept is relatively easy to understand. It's just about putting this into action, because the hardest part is going to be finding the two series that we need. So to apply the test for convergence or divergence, we need to do one of the following. We either need to find a bigger series that converges. If the larger series converges, your smaller series also has to converge, or you need to find a smaller series that diverges. And if that's the case, the smaller series diverges, the larger one that we already have is going to diverge. That may not make a lot of sense. Let that sink in, read it over. When we do some examples, hopefully it'll make sense. All right, and you can read this note here: because the convergence of a series is not dependent upon the first several terms. You could have something where the terms kind of switch places, but like I said, if starting at like 4, this pattern holds, then you're going to be okay. It's really what happens towards the extremes. All right. So what we want to do is we want to take a look at the series that we have, and then we want to find something which is similar to that series, but it's not the same. And we can kind of generalize. So if we take a look at this, what you want to do is you kind of want to take a guess as to what you think the series is going to do. If we take a look at this series right here, we want to determine whether this is convergent or divergent. If you take a look at this series, it's 1 over 2 plus 3 to the n. 3 to the n grows very, very fast. It's not the fastest thing, but it does grow fast. So I would assume that this thing is probably going to approach 0 fast enough that it will converge, but we would still need to prove that. Well, the idea is what I'm going to do is I'm going to find a series which is similar to this. I'm assuming that this converges, so I want to find something which is a greater series than this one, which also converges. And then if that's the case, I can say definitively that this one will converge. Okay, what do I mean? So that this series right here resembles 1 over 3 to the n. This 2 really kind of becomes irrelevant as these terms go way off to infinity. It looks like 1 over 3 to the n. 1 over 3 to the n, we should recognize that we could rewrite, we'll call this b sub n. This is what we're going to compare. This is our a sub n. This is our original series. We're going to call this b sub n. In this case, we're trying to say that a sub n is less than or equal to b sub n. And is that true? We'll call this our a sub n because it's the given series. Typically, we call a sub n the given series, and b sub n is our second one. So b sub n here is 1 over 3 to the n. Well, we could write that as the sum n equals 1 to infinity of 1/3 to the n, which we should know as a geometric series. So what we can say about b sub n here is for b sub n, oops, come on, there we go. For b sub n, r is 1/3, which we know is less than 1. Therefore, b sub n is convergent. And it's convergent because it's a geometric series. R is less than 1. We are good there. And because we know B sub n is convergent, all we have to do is show that B sub n now is the greater series, and therefore A sub n, which is less than B sub n, has to also be convergent. Well, that's pretty easy to see in this case. There's not a lot to have to prove here. The denominator here is 3 to the n. The denominator here is 2 plus 3 to the n. This is a bigger denominator. Numerators are identical, so a bigger denominator typically means a smaller fraction, a smaller number. So we can definitively say that this is true, since A sub n is less than or equal to B sub n for all n, then A sub n is also convergent. All right, hopefully that makes sense. The hardest part here is I gave this to you in this case. It's going to be trying to figure this part out right here. What am I going to compare my original series to? That's going to be the most difficult part. All right, let's take a look at another example. Okay, and what it says is we've got the series n over n plus 1. We're going to call this our A sub n. What we need to do is we need to try and figure out what we compare this to. Well, that would normally be the case in any other circumstance. One thing we forgot to do, and I didn't really do it up at the top, we probably should have done it in the previous problem. Well, actually we did. I kind of mentioned it, but we didn't say specifically. You could use some kind of a comparison test on this, but why don't we just try taking the limit first? If we take the limit as n approaches infinity of n over n plus 1, that's 1. This is the nth term test for divergence. This is automatically divergent. So you don't always have to do a comparison test or something else. Remember, always try this one first, because if this works, you're done. All right, third example. This one we actually have to do some work on. So let's see, we've got the sum of 1 over the square root of n to the 5th plus 7. So we'll call this A sub n. What it looks like is I'm going to look for the dominant term in the denominator and the dominant term in the numerator and kind of see how that plays out. Well, 1 is just 1, so that's not a big deal. The dominant piece down here is really this n to the 5th, but it's the square root. So the dominant part of the denominator is really going to be an n to the 5 halves. This plus 7 under here, again, as this thing gets extremely large and goes off to infinity, is kind of irrelevant. So we're just going to look at the dominant term, and the fact that this is a plus 7 means that this denominator is going to get bigger. So if I let b sub n equal the sum of 1 over n to the 5 halves power, this, I happen to know, is a p series where p equals 5 halves. And since p is greater than 1, this one is b sub n is convergent. Okay, and since I know that b sub n is convergent and b sub n is a greater series than this one, how do I know that? Well, this denominator is getting bigger, so it's a smaller value than this one. Bigger denominator, smaller fraction, so this is going to be a bigger series overall. So we can say that b sub n is greater than or equal to a sub n. Same thing as saying a sub n is less than or equal to b sub n. Doesn't matter. Therefore, a sub n is also convergent. Again, this one right here was our given series. We think this is going to converge because it looks like the dominant term is a 1 over n to the 5 halves, which is a p series. So we're going to use that as our comparison. And we do know that 1 over n to the 5 halves is a p series. P equals 5 halves greater than 1. This is the bigger series. This is convergent. So any smaller series, which this one is also going to be convergent. All right, let's determine the convergence or divergence of this one. Okay, this one's a little bit different because we have a numerator here which isn't constant. We're still going to call it a sub n. The dominant term in the denominator still looks like it's an n to the, in this case, 1/2 power, right? So we're going to let b sub n equal the sum of 1 over n to the 1/2 power. This one is a p series where p is 1/2, and this is less than 1, which makes this one a divergent series. That is divergent. So if this is divergent, this b sub n, we're hoping that this a sub n is bigger than that, because if it is, we can say it's divergent. If this is a less series than this one, we can't say anything about it using this in particular thing. We'd have to find another way. But the denominators here are identical. Oops, that should start at a 2. The denominators here are identical. This one's numerator is the natural log of n. So past 2, or from 2 on, this is going to be a bigger fraction than this one is. So this is a bigger series. So a sub n is greater than or equal to b sub n. Therefore, a sub n is also divergent. Technically, I think this is going to be the bigger series once this is past e. So basically from 3 on, because e is 2.71. So anything past 3, but this starts at 2. And like we said before, it can start at 2. This actually is a lesser series than this one at 2, but then once it gets to 3 and from 3 on, it is always going to be bigger. And we're really only interested in what happens towards the extreme of this thing anyway. That's going to determine the convergence or divergence. All right. Hopefully this is starting to make some sense. Moving on. Okay, this one's a little bit different looking. I've got 1 over n to the square root of n. I believe this is what's called an iterated function, because you've got a base and an exponent, which are both changing at this with the same as n gets bigger. You're plugging in the same thing for both of them. So we'll call this a sub n. All right, so now let's think about this. This value here is going to get bigger. So if I plug in 1, I'm going to get n to the first. If I plug in 2, I get n to the square root of 2. If I plug in n equals 4, I get n squared. This power here is going to keep getting bigger. If I compare this to something where this doesn't change, well, I can compare it to 1 over n to some power. I got to figure out what power that would be, where this doesn't change. So my assumption is, because this is going to be a huge denominator, this is going to get big very, very fast, since I'm raising a base to basically the square root of its own power. It's going to get very big very fast. I'm assuming this is probably going to converge. So let's compare this to something which we already know converges. 1 over n does not converge, it's divergent. I wouldn't want to use that one. I could, however, use 1 over n squared. I know that that converges. And this 2 is going to stay the same. So what's going to happen is, as I start plugging numbers in here for n, this denominator is going to go up by squaring its denominators. This one, as I start plugging in n, I'm going to go more than squaring its denominators, because once I get to n equals, what, 3? No, 9. So this would be 9 to the third power. This one's only going to be 9 to the second power. This denominator will be bigger, which means this whole fraction here would be smaller. So a sub n, after a certain point, is going to be less than b sub n. So we're going to say a sub n is going to be less than or equal to b sub n, which is good because we know that this one here is a p-series which converges, which means that a sub n, since it's less, will also converge. So let's just write that down. And I think the changing point here is probably at 4, from 4 on, I think. Yeah, that should be right. So here we know that p equals 2, greater than 1, which makes b sub n convergent. A sub n will be less than or equal to b sub n for n greater than or equal to 4. Because then I would have 4 to the second, 4 to the second. Anything past that, this is going to be the bigger denominator, so a sub n will be smaller. Yeah, that's right. And since I can say that, therefore, a sub n is also convergent. All right. Like I said, the hardest part is going to be picking out what you're comparing to. All right, hopefully you can look at this one and think, oh, this is pretty easy to see. Again, this little plus 2, as these numbers go way off to infinity, but basically doesn't mean too much. 7 over 6 to the n power, 7 to the n over 6 to the n. It looks like we're going to compare this thing, this a sub n. We're going to let b sub n equal 7 sixths to the n power. And that one is definitely geometric, where r is 7 sixths. We know that that is a greater value than 1. Therefore, b sub n is divergent. Now we just need to show that this one is a greater value. 7 to the n plus 2 is going to be bigger than 7 to the n because the denominators are both 6 to the n. So a sub n is going to be a greater sum. So b sub n, or excuse me, a sub n is greater than or equal to b sub n. Therefore, since b sub n is divergent, a sub n is also divergent. And again, hopefully that is starting to make some sense. Like I said, the hardest part of the direct comparison test, which is which one this is going to be figuring out what you're going to compare it to. You're basically looking for the dominant terms on the top and the bottom, comparing them, and then again, making some kind of an assumption what you want the function to be, and that kind of helps you to figure out what you're going to compare it to, because you want to compare it to something that would work. If you compare it to something that would work, but it gives you the wrong thing, like if you compare something and you want the function to be convergent, but you find that your series is actually less than the other series, then you got to try something else. All right, we are going to come back with a second video, and we will talk about the limit comparison test.